Hello, in this video we're going to learn how to add and subtract radical expressions. And the first example I'd like to begin is that when we do this, we want to think of like terms, right? When we learned how to combine like terms, the terms had to be similar, okay? Like numbers go with numbers, x's go with x's, y's go with y's, x squareds go with x squareds, etc. Okay? So when we add or subtract radicals, what has to be the same is the radical. So radical 7 is common in all three terms. And the coefficient here is 1. So we can go ahead and combine all of the coefficients, okay, and then we can get one term. All right? So when we do that, okay, again, we have 1 plus 2 is going to give me 3 radical 7. And then we can go ahead and combine 3 and 9, which will give me 12 radical 7. Okay? And we can't simplify that anymore, so this will be the answer. All right? Okay. So let's look at another example. You have 1/2 square root of d plus 3/4 square root of d plus 3/5 square root of d. Okay, so notice that all of the coefficients are fractions and they're all different. Okay, so we're going to do this is essentially what we're adding, right? We're adding those three fractions. And in order to do that, we're going to have to find the LCD. Okay, so it's quite evident that we have to, whoops, I'm sorry. So I'm going to find the LCD, the least common denominator. And we could do that by several ways we can do this, okay? The common denominator is going to be 20, okay? So when we do this, okay, remember, if you want to find the common denominator, okay, you can make separate columns, 2, then you got 4, and then you have 5. I'm so sorry, this pen keeps slipping. Here we go. And we want to make multiples of all of those numbers, okay? And we do that, we have 2, 4, 6, 8, 10, 12, 14, 16, 18, and then we have 20. Here we have 4, 8, 12, 16, 20, 24, 28. Here we have 5, 10, 15, 20, 25. What a number pairs in each row first? It's going to be 20. And that is your LCD. So your LCD is going to equal 20. All right? So when we do this, we're going to multiply this fraction, this denominator, by something in order to get 20. And the only way that's going to happen, it has to be 10. But then you're going to do the top by 10 as well. Here, we have to multiply 4 times what? 4 times 5 will in fact give me 20. We have to times the numerator as well. And here, 5 times 4 gives me 20. So in reality, we multiply all these numbers. 10 times 1 is 10. 2 times 10 is 20. Plus 3 times 5 is 15 over 20. Plus 3 times 4 is 12 over 20. Okay? So what this problem now becomes is this now becomes you have 10 over 20 square root of d plus 15 over 20 square root of d plus 12 over 20 square root of d. Okay, now we want to add all of the coefficients. Well, the denominator is the same, so when we add 10 plus 15 plus 12, we in fact get 37 over 20 square root of d, and that's the answer. So this problem was just basically, can you add fractions with different denominators? All right? Okay, so let's do another example on the next slide, okay? And here we have 4. All right, so we have this particular problem, okay? And we want to look, all right, we want to combine like terms. Now what we have to look under is under the radical. This is where it matters, okay? So 11x is common in all of the radicals, in all of the terms, okay? So all we got to do now is basically combine the coefficients. We have 4 plus 3 plus 27. Also notice that the index of cube root here is the same. Okay, so what we're going to do is we're going to add 4 plus 3 plus 24. And when you do that, you're going to get 31. And that would be the answer for that one. Okay? So that was pretty straightforward, right? Okay, now, what if you get this? Okay, when we want to add radicals that are different, we're going to have to break them down. And you notice we're taking the square root. So when you break this down, I want you to think of two numbers that multiply to give me 12. So one of them is a perfect square, okay? And when we do this, I can think of a number, 4 times the square root of 3. Why did I pick 4 and 3 rather than 2 times 12? Because 4 is a perfect square. We can actually take the square root of that, okay? And that is going to simplify that radical pretty nicely, okay? And then we're going to do the same here. I want you to think of two numbers that multiply together to get 27. I can think of 9 and 3. Why did I pick 9 and 3? Because 9 is a perfect square. And 9 and 3 is the only two to give you 27 anyway. Okay? Other than 1 and 27. So now we have perfect squares here and here. So we can go ahead and take those perfect squares and say, okay, the square root of 4 is 2 times the square root of 3. Square root of 9 is 3 times the square root of 3. So now everything that's not under the radical gets multiplied with each other. So 2 times, I would say, we add the coefficients. Now we're multiplying, sorry. So we have 2 square root of 3 plus 3 square root of 3, okay? So what this is really saying is, when you simplify this is what it really comes down to. Let me go ahead and write this first. 2 times the square root of 3 is 2 radical 3, plus 3 times the square root of 3 is 3 radical 3, okay? And then I meant you can add the coefficients now. So 2 plus 3 is going to give you 5, okay? It's going to give you 5 square root of 3. And that would be your answer. Okay? All right. So let's do another one. I think this is 5, right? Yeah, 5. And we're going to take the square root of 50, x to the 7th, plus x as the square root of 32, x to the 5th power. So we're going to have to simplify these radicals. What this is really saying is we're taking the square root of 50 times the square root of x to the 7th plus x, okay, times the square root of 32 times the square root of x to the 5th power. That's how, if we treat each term separately, we can break them down. Now the square root of 50 can be broken down into two numbers that get multiplied with each other. One of them is going to be a perfect square. So rather than using 5 and 10, 5 and 10 is really not going to allow us to simplify it. So we're going to have to choose a different combination. And I'm going to pick 25 and 2 instead. Why? Because 25 is a perfect square. And then remember, when we did this, okay, when we have an odd exponent, a base raised to an odd exponent, we're going to make it one less, and that's going to give me my perfect square, because x to the 6th power is a perfect square, because x to the 3rd times x to the 3rd, when you add the exponents, gets you 6. Okay, so far we have this perfect square and this perfect square. Then we have plus, and then x, and now we need to break this down, okay, which is going to be square root of 32. Okay, can you think of two numbers that get multiplied so that one of them is a perfect square? And I could think of 16 times 2. That would give me 16 is a perfect square. Okay, and then I can break this down, and I could, like I said, make it one less, and you're going to get your perfect square. So we said 16 is a perfect square, and so is that. So if you have x to the 5th power is an odd exponent. So if we drop it down one exponent, we get the nearest perfect square, and then we can identify what that is and simplify it. So now we're going to identify all the perfect squares. Okay, and these are the ones I want you to simplify. Take the perfect square. So square root of 25 is 5. Everything else. Square root of x to the 6th is x to the 3rd, because when you do x to the 3rd times x to the 3rd, you get x to the 6th. Okay? Square root of 16 is 4. Square root of x to the 4th power is x squared. And now we've simplified everything we possibly can. So now we're going to multiply everything that's not under the radical. That's 5, x cubed, x, 4, and x squared. So 5 times 4 is 20. Okay, so I'm going to do that first. It's 20. Excuse me, we have the plus sign is in the middle. I meant to say 5 times x cubed. So let me do this. I kind of jumped ahead. 5x cubed. So what we're doing is we're multiplying these two together. And then there's the plus sign, and then we're going to do these two together. Okay? Sorry about that. I was actually trying to figure out something here, so I apologize for that pause. Okay, let's do another example. I'm going to have to do it on the next slide for more room. Okay, so let's go ahead and do this one. Okay, for the fourth root of 32 plus the fourth root of 162 plus the fourth root of 2 over 81. And we're going to simplify this, okay? So the first thing we want to do is that we got to think of fourth root. What does that mean? Well, that means a number times itself 4 times, okay? So you got to think a little differently here, right? When we break down the radicals, okay, we got to think of fourth roots, okay? Well, the only fourth root that I can think of that times itself twice is going to be 16. Why is 16 a fourth root? 2 times 2 is 4, times 2 is 8, times 2 is 16. Okay? So, again, you have to think a little differently because you're thinking of the fourth root, not the square root. Alright? Then we're going to have to break this down, and we're going to think of the fourth root of what 2 numbers multiply to give me 162 so that one of them is a fourth root. Okay? And actually it's going to be 81. So you go, it would really help to know the basic fourth roots. So you can write those down, and 81 is definitely a common fourth root. So if you identify those ahead of time, you have the list, and then you can kind of, look at the little list you have and then go from there. And then you can list all the common perfect cubes, the common perfect squares, the common fifth roots, like the fifth root of 32, that's a common one, okay? So maybe it'd be helpful to have those handy, okay? And then, of course, we want to do the last term. And the last term is just basically stating this. The fourth root of 2, excuse me, oops, let's rewrite this, I'm sorry. The fourth root of 2 over the fourth root of 81. Okay, because you can write those as separate. When you have a square root of a fraction, when you have any nth root of a fraction, you can take the nth root of that numerator and the nth root of that denominator. So in this case, we're taking the fourth root of 2 over 81. So you take the fourth root of 2 and the fourth root of 81 in fraction form. It's the equivalency. Okay? And that stems from this, just so you know. Okay? So it stems from this. So let's say you had the nth root of a over b, then that's equivalent to the nth root of a over the nth root of b. Okay, does that make sense? That's what I did over here. All right? So just kind of keep that in mind. It's a little bit of a property that we need to know. Okay? So let's go ahead and go back to the left and finish the problem. The fourth root of 16 is going to be 2. Okay? It's going to be 2. Now we can't take the fourth root of 2 because that's just going to be a decimal. We don't want to do that. But we can take the fourth root of 81. So these are perfect fourth roots, right? So the fourth root of 81, okay, okay. So what we want to do here is that we want to go ahead and add all the coefficients, okay? So we're going to be really careful here. There's a plus. So let's kind of write the 2 times the fourth root of 2 is equivalent to this. 3 times the fourth root of 2 is that, plus fourth root of 2 over 3. Okay? And we can also write this as one third the fourth root of 2. Okay? 1/3. Alright? And now we can add all the coefficients. We can add all the coefficients of 2, 3, and 1/3. So when we do that, okay, 2 plus 3 is 5 plus 1/3. So then we're going to have to write that as over 1 and find the common denominator. Okay? So when we do that, okay, we're going to multiply this side by 3 because the LCD is going to be 3. All right, and when we do that, that's going to give me 15 over 3 plus 1/3. That's going to give me 16 over 3. So when I add all the coefficients, I'm going to get 16 over 3 times the fourth root of 2. And that would actually be the final answer. So a little bit of a process, I know, but we can go ahead and simplify that. Okay? So that is how you would do that. Okay, I hope that you found this video to be very helpful, and thank you for watching.